Hey everyone, and welcome to this explainer. Today, we're diving into a really fascinating research paper that reveals exactly why constantly tweaking and adjusting machine learning systems is actually, well, a pretty terrible idea. And more importantly, we'll see how a highly strategic, lazy algorithm completely solves this massive problem. If you've ever wondered how tech giants manage thousands of competing parameters without their servers literally melting down, you are definitely in the right place. So, let's just jump right in. To make sense of this highly technical research, we're going to break it down into 5 quick steps. First, we'll look at moving beyond binary machine learning, then understand the true cost of constant change. After that, we'll unpack the incredibly clever Lazy Graph LinUCB algorithm, see how it exploits graph structures, and finally, we'll wrap up with a real-world fairness tuning proof.
All right, part 1, Beyond Binary Machine Learning. Let's talk about the shift toward continuous systems. So think about the massive recommender systems we interact with every single day, like the one serving up articles on your newsfeed or videos on social media. That system has to juggle a ton of conflicting targets. I mean, it wants to increase the diversity of what it shows you, right? But doing that might actually degrade strict relevance. Or it wants to enforce certain structural constraints, but that could spike system latency or worse, tank revenue. This introduces a massive optimization challenge because you really can't just maximize one metric without hurting another. It's a delicate balancing act.
Now, historically, researchers treated these trade-offs like basic binary switches. A setting was either on or off, a 1 or a 0. But this paper points out a major flaw there. That just doesn't capture reality. Real-world hyperparameters aren't light switches. They're more like continuous volume dials. For example, you might want to set a fairness threshold, like an allowable gap in true positive rates, to exactly 0.7. Or maybe you want to fine-tune a diversity mixing rate anywhere on a sliding scale between 0 and 1. This paper actually extends the entire framework of competing objectives to accommodate these continuous dials. It's way more realistic for sure, but as you might guess, it introduces a whole new set of really complex problems.
Which brings us to part 2, the cost of constant change. Let's look at the actual price of all this instability.
What happens when a system tries to adjust those continuous dials all the time? Well, in a word, chaos. Every single time you turn that continuous dial, it incurs what the researchers call a movement cost. See, in continuous control systems, you can't just rapidly change parameters for free. Turning a dial takes computational effort, it causes cache invalidations, and it triggers all sorts of downstream recomputations. So we're left with this serious tension between exploration, turning the dial just to see what happens, and stability, which means keeping the system quiet to avoid racking up all these movement penalties. The researchers literally hit the nail on the head here, noting that in continuous control systems, rapid parameter changes are highly disruptive, and standard algorithms, they completely fail here. If you throw standard optimization like a normal LinUCB algorithm at this problem, it's just going to constantly jitter. Every time even a tiny bit of noisy new data trickles in, the algorithm recalculates a slightly different optimal state and tweaks the dial. This incurs massive, snowballing movement costs that are just flat-out prohibitive if you're running a large-scale production system. All right, part 3, Lazy Graph LinUCB. This is where we learn how to balance that exploration with much-needed stability. The core solution here is absolutely brilliant, and it's called lazy updates. Instead of constantly jittering and tweaking, the algorithm just freezes the active policy. It completely refuses to move the dials until enough new data has been collected to definitively justify the cost of making a switch. Think of it like a smart home thermostat. You wouldn't tweak your AC every single second just because the room temperature fluctuated by 1/10 of a degree, right? No. You wait for a noticeable, measurable temperature shift before spending the mechanical energy to turn the system on. This algorithm does exactly that, by tracking the determinant of its covariance matrix. In plain English, that matrix is just tracking the algorithm's own uncertainty about the optimal setting. The system stubbornly refuses to move until the new incoming data literally halves that uncertainty, meaning the information gain essentially doubles. Only then does it finally pull the trigger and update the dials. And to make this even more efficient, they use a specific graph structure. If we look right in the center here, we've got node I shaded in purple. Let's say that represents one specific objective. Its immediate local neighborhood only includes nodes J, L, and M. The researchers apply what's known as a graph-structured loss. Mathematically, this means if you want to calculate the gradient, or the performance loss, for that central node I, you strictly only need data from those direct connected neighbors. Now look way off to the side at nodes X and Y. Because of this graph-structured loss, changes happening over at those distant, non-neighboring nodes have absolutely zero effect on our purple node I. By isolating the math to just J, L, and M, they mathematically prove the gradient is totally independent of X and Y. This is a massive deal because it turns what would normally be huge, system-wide matrix calculations into incredibly simple, lightweight local updates. Moving on to part 4, exploiting graphs to maximize efficiency. Let's see how deep this rabbit hole goes. In really dense systems, you have highly correlated objectives, which means overlapping components start to naturally emerge. Imagine two overlapping triangles, or what we call cliques. Here we have clique 1, outlined in red, connecting nodes 1, 2, and 3. Then we have clique 2 in blue, connecting nodes 2, 3, and 4. Notice how nodes 2 and 3 are sitting right smack in the middle, overlapping both cliques? In a dense system, these objectives share underlying physics or latent factors. Now, a standard, naive algorithm would treat that red clique and that blue clique as totally separate things, basically doing all the heavy computational math for nodes 2 and 3 twice. But the researchers introduced a joint estimator. By treating this whole network as a factor graph, the algorithm cleverly projects the parameters of those overlapping middle nodes into a shared latent space. It's a brilliant mathematical trick that completely avoids redundant exploration. By disentangling those shared parameters, it drastically reduces the sheer volume of math the system has to crunch, because the information it learns in the red clique directly helps it solve the blue clique. And that joint estimator, that's just one of 3 advanced mechanisms they tested. The researchers also proved that in sparse graphs, you can run asynchronous updates, meaning if one tiny part of the network learns something new, it just quietly updates its own local neighborhood. It doesn't force the entire global system to pause and synchronize. Finally, they showed that even if you walk in completely blind and don't know the graph structure at all, you can use an adapter routine with a quick warm-up phase to actually learn the connections from scratch entirely from the raw data. Okay, part 5, real-world fairness tuning. Let's look at the hard proof and see this in action. The proof is incredibly stark when you look at the empirical metrics. Check out the chart on the left, graphing the action value against the number of rounds. You see that erratic gray waveform jumping around like crazy, oscillating back and forth between negative 0.6 and 0.0 at every single step? That is your standard algorithm overreacting to noisy data, completely burning through movement costs. But then, look at that thick orange line. That's our lazy algorithm. It makes an update, and then it just completely freezes into a flat, straight, horizontal line until enough actual new information forces it to take another step. Now, glance at the chart on the right, which maps the cumulative movement cost over those exact same 300 rounds. The consequence is huge. That gray line shows linear growth. It just keeps shooting straight up. Meanwhile, the orange lazy cost line curves and completely flattens out logarithmically. This mathematically proves it achieves sublinear regret in system costs, meaning you get the exact same predictive accuracy, but with a frankly massive reduction in physical taxation on your system.
And honestly, it gets even better when you apply those advanced graph mechanics we talked about. This chart compares different versions of the lazy algorithm itself. The orange line is the global lazy strategy, but check out the dark blue line below it. That's the async lazy algorithm. Notice the lighter colored shading around the solid lines? That standard error shading proves that the async method isn't just a little cheaper on a lucky run. It's reliably and consistently cheaper across the board. By exploiting the sparse graph structure and using local triggers, so nodes only update themselves and their direct neighbors, they completely crush the movement costs. You can literally see a 3.1 times reduction visualized right there in the massive gap between the top gray baseline and the bottom blue line, all because stable parts of the system weren't forced into a needless update just because a volatile neighbor had a hiccup.
So, where does this all culminate? In a real-world fairness tuning test. The researchers took the adult census dataset and trained a classifier to predict whether individuals make over $50,000 a year. The algorithm was given a continuous control problem. Tune a decision threshold anywhere between 0 and 1 to maximize prediction accuracy while simultaneously minimizing the equal opportunity fairness gap across different demographic groups. Look at the left chart. Once again, that standard algorithm, the gray line, is oscillating wildly, totally struggling with batch noise as it blindly hunts for the optimal threshold. But our dark blue line, the lazy algorithm, shows a beautifully stable learning curve that smoothly converges exactly where it needs to be, right around that 0.9 threshold region. And the chart on the right? That's the final verdict. When measuring actual operational efficiency, the standard approach racked up a massive cost score of 14.0. The lazy approach? Just 2.5. That is a 5.7 times reduction in operational churn, all while hitting the exact same optimization targets.
So, to quickly summarize what we've covered in this explainer, the research team successfully pushed objective optimization past simple binary switches into realistic, continuous states. They built a highly efficient, lazy graph-based algorithm to completely kill system jitter. They designed structural exploitations like asynchronous updates and joint estimators to squeeze out absolutely every drop of efficiency. And they proved it all empirically, delivering massive cost reductions in real-world scenarios.
Now that we've seen just how incredibly powerful holding back, freezing your actions, and actually waiting for the right data can be, it really leaves you wondering, where else in the tech world, or maybe even in our own daily decision-making, could a little strategic laziness save millions in wasted energy? Thanks so much for joining me on this explainer, and keep questioning the algorithms that run our world.